Good morning to all of you. Today in this online video lecture, we are going to solve a problem on steady flow energy equation. So through this problem, we will understand how to apply the steady flow energy equation for steady flow device like a diffuser. Let us go to the problem. Let me read out the problem. Air at 10 degrees Celsius and 80 kilopascal enters the diffuser of a jet engine steadily with a velocity of 200 meter per second. Right, so this problem talks about a diffuser of a jet engine. Uh, Mainly all the parts of the jet engine can be considered as a steady flow device. So diffuser is also a steady flow device, right? Diffuser is a component where the flow velocity decreases and the pressure increases. So let me draw a simple sketch of a diffuser. Normally a diffuser will have uh, less area at the inlet and more area at the outlet. So let me draw a diffuser. So this may be taken as a simple sketch of a diffuser where the inlet flow area is less and the outlet flow area is more, right? The flow occurs in this direction, and let us take 1 as the inlet condition and 2 as the exit condition of the diffuser. According to the problem, the temperature at the inlet is given as 10 degree. T1 is equal to 10 degrees Celsius, and then the pressure at the inlet, pressure of the air at the inlet is given as P1 equal to 80 kilopascal, right? And then the velocity at the inlet of the diffuser is 200 meter per second, and the inlet flow area or cross section area at the inlet of the diffuser is given as A1 equal to 0.4 meter square. Okay, and then if you look at the next sentence of the problem, it is given like this: the air leaves the diffuser with the velocity. That means the velocity at the exit of the diffuser V2 is very small compared with the inlet velocity. So inlet velocity is V1. When we compare V2 with V1, V2 is very small. So what we can understand from this statement, we can understand that V2 is very small when compared to V1. So V2 can be neglected. In solving this problem, V2 can be neglected. That is what we can understand by this statement. Okay, so these are the data given for this problem, and you are asked to determine the mass flow rate of the air and the temperature of the air leaving the diffuser. So mass flow rate, we need to find out the mass flow rate m dot and the temperature of the air leaving T2, right? Now before we solve this problem, let us convert the temperature from degree Celsius, given temperature T1, from degree Celsius to Kelvin. So whenever I substitute the value of temperature in the steady flow energy equation, it should be in absolute temperature or Kelvin. So I convert this to Kelvin by adding 273. So you will get 283 Kelvin, right? Now, in solving this problem, we are going to use two equations. One is a mass balance equation. So from mass balance equation, I can determine the value of mass flow rate m dot. So let us write the mass balance equation. So m dot is equal to rho 1 a1 v1 density, area and velocity at the inlet. This is also equal to rho 2 a2 v2, right? So since this diffuser is a steady flow device, the mass flow entering the device is equal to mass flow leaving the device. So I can find out the value of m dot using rho 1 a1 v1, or m dot can be determined using rho 2 a2 v2. Here let me use this expression m dot mass flow rate through the diffuser m dot is equal to rho 1 a1 v1, because already I know the value of a1 and v1. Only term to be determined is rho 1. So let me use this expression m dot equal to rho 1 a1 v1. In this problem, the value of rho 1 is the density of the flow at the inlet. Density rho 1 is not given in this problem, so I need to find out. So to determine the density, I am going to use the equation of state, or the ideal gas equation. So let me write down the equation of state. Equation of state is a familiar expression to everyone. So I'll write P V is equal to M R T. So when I bring the V to the right hand side, I will write P is equal to M by V. Mass by volume is density rho RT. So from this I will get the expression for rho, or density, which is equal to P by RT. Okay. So if I want to find the value of rho 1, I need to substitute P1 and T1. R is a constant. Okay, for air, we should know the value of R. For air, the gas constant R is equal to 0.287 kilojoule per kg Kelvin. So here in this problem, the value of P1 and T1 are known. We can substitute the value of R to get the value of rho 1. So let me go to the next page. Right. So here I will write rho 1 is equal to P1 by RT1. The given value of P1 is 80 kilopascal. R, we know the value of R, 0.287, and the temperature is 283 Kelvin. So I'll get the value of rho 1 as 0.984 kilogram per meter cube. So I got the value of rho 1. Next step, I'll find out the mass flow rate. M dot is equal to rho 1 A1 V1. Right? So I'll once again write down rho 1 A1 V1. The value of rho 1 is 0.984. A1, let me go to the previous slide. A1 is 0.4 and V1 is 200. So let me substitute those values, 0.4 into 200, which gives me a value of 78.72 kg per second, kilogram per second. So this is the mass flow rate through the diffuser. So this is the answer for the first question, mass flow rate. Okay. Okay. So next we will move on to uh, the next question, that is to find out the temperature at the exit, temperature at the exit of the diffuser. Right. So for finding out the temperature, I am going to apply the steady flow energy equation. Let me write the SFEE, short form of steady flow energy equation, SFEE. I'll write the full equation, dq by dt plus m dot into h1 plus v1 square by 2 plus z1g is equal to dws by dt, rate of shaft work, plus m dot into h2 plus v2 square by 2 plus z2g. Right. In a steady flow device like diffuser, the value of z1 and z2 are almost equal. So I can cancel out these two terms, z1 and z2. So these are the assumptions we make. So what are the assumptions we make for simplifying this steady flow energy equation? First assumption is we assume that z1 is equal to z2, and then we assume that there is no heat loss or heat transfer during the flow process. So I'll take dq by dt is equal to 0, right? So these are the assumptions we make for this diffuser. And in a diffuser, we should know that there is no work transfer involved. That means shaft work, dws by dt, rate of shaft work. So this rate of shaft work is absent for a device like a diffuser. So this is not an assumption, this is the fact. So dws by dt is equal to 0 for a diffuser. And the third point to be noted here, as given in the question, the value of V2, the value of V2 is very small when compared to the value of V1. So I can neglect this V1, V2, I can neglect V2. dq by dt is assumed to be 0, and similarly dws by dt is also equal to 0. Okay, so after making these assumptions and applying these following conditions, the steady flow energy equation will get simplified to this form. Now the steady flow energy equation will take this form, m dot into h1 plus v1 square by 2 is equal to m dot into h2. All the other terms are cancelled or neglected. Okay, you can look at this equation. We have remaining m dot into h1 plus v1 square by 2 on the left hand side. In the right hand side you have m dot into h2. Okay, so now what I can do, we have to find out a temperature. So I am going to write down the enthalpy in terms of temperature. So let me go to the next slide. Right, so I'll write m dot enthalpy for a perfect gas can be written as Cp into T, specific enthalpy. So H1 can be written as Cp into T1 plus V1 square by 2. On the right hand side, similarly, H2 can be written as m dot Cp into T2. Okay, so if you look at this equation, I can cancel out m dot from both sides. Okay, so now we need to get the value of T2. I substitute all the other values. Cp for a gas, for air, Cp value is equal to 1005 joule per kilogram Kelvin. Okay, so let me substitute 1005 into T1 283 plus V1 square 200 square by 2 is equal to 1005 into T2. So T2 is the only unknown. So upon simplification, I will get the value of T2 as 302.9 Kelvin. So this is the temperature of the flow leaving the diffuser. Right. Thank you very much for watching the video. If you have any doubts, you can clarify in the classroom next day. Thank you very much.